Hey everybody, welcome. All right, today we are still in Unit 4. We're in the second half of it. We're going to be looking at greatest common factor, and then also how do we use a factor tree to find the prime factors. So this is something that we're going to use to find the greatest common factor in other scenarios. Our essential question for today is, what is a factor tree and how does it help us find the greatest common factor? Let's take a look. Okay, so if we've got factors being numbers that are going to multiply to be a original number, so we think of two values that multiply to be a bigger number, those two values are the factors of that number, or they're at least an example of the factors. So when we think about the factors of 20, I am asking you what numbers multiply to be 20. So when we start listing these, you can usually start with 1. So we say 1 and 20. 2 and 10, 4 times 5, and then if I start listing numbers that have already been listed, like 5 and 4, I know I've gone too far, so I don't need to list them again. However, the negative versions also exist, so negative 1 times negative 20 would also multiply to be 20, negative 2, negative 10, and negative 4, negative 5. The negative stuff you probably didn't do before. If you have done factoring before, it's kind of new for us. We're mostly going to focus on the positive factors, but we do need to be aware that the negative ones exist, particularly for factoring a negative number. All right, so let's factor each of the following values. Pause the video, try and do all of them, come back when you're ready to see the factors. Okay, so for 100, we've got 1, 2, 4, 5, 8, 9, 10. So we got 10 times 10, and then we got 5 times 20, 4 times 25, 2 times 50, and 1 times 100. For 42, we got 1 and 42. We got 2 and 21. We've got 3 and 14. We got, let's see, 2, and just 6 and 7. All right, so 1, 2, 3, 6, 7, 14, 21, 42. For 7, there's just 1 and 7. This is a number that we would call a prime number. So when a number's factors are only itself and 1, for positive numbers anyway. And notice I'm not listing the negative ones at the moment, but just know that every factor we list, the negative version is also a factor. But prime numbers, the only factors are itself and 1, so 7 is a prime number. 144, so we got 1, 2, we got 3, 4, 6, 8 would be a factor as well. Should have my calculator out to check that. Yes, it is. So we get 8, 9, 12. Now 12 is an important one because when you're doing these lists, so I'll do the 144 list over here. A trick I have is if you do the square root of that number, and this goes for any number, it doesn't have to be a square number, but if you do the square root of 144, you get 12. So that means that if I were to try and test every single number to try and find factors, so I'm doing like a guess and check because I can't remember my times tables, I only need to go as far as 12. So whatever the square root is, that's as far as you need to go in terms of testing. So like 144 divided by 1 is 144. 144 divided by 2 is 72. 144 divided by 3 is 48. 144 divided by 4 is 36. 144 divided by 5 doesn't work, so I'm like, nope, that doesn't work. 6 times 24, 7, does 7 work? 144 divided by 7, nope. 144 divided by 8 is 18, so 7 does not work. 18, 9 times 16, 10 does not work. 11 does not work, and then 12 times 12. And at this point, we're done. So my numbers would start going up again. So my pairs are a to 12, we got 16, 18, 24, 36, 48, 72, 144. So just remember, square root the number, that'll tell you what's the highest factor you have to test to. So like if I do the square root of positive 24, can't do square root of a negative number, so you do the square root of the positive number. So minus 24. Square root of 24 would be 4.89. So 1, 2, 3, 4, and then like 4.89 would be down here, but that can't be a factor anyway. So I would test 1 through 4. So 1 times negative 24, 2 times negative 12, 3 times negative 8, 4 times negative 6, and then I would keep going. So like 6 times negative 4, 8 times negative 3, 12 times negative 2, and 24 times negative 1. And that would be my full list of factors. For negative 36, 1 times minus 36, 2 times minus 18, 3 times minus 12, 4 times minus 9, 5 doesn't work, 6 times negative 6, and then the other way as well. So we got 9 times negative 4, we got 12 times negative 3, 18 times negative 2, and 36 times negative 1. That would be my full list of factors. All right, factor trees I really like. So first thing we need to know for factor trees is our prime numbers. So the ones that have only itself one as a factor. So that is 2, 3, and fun fact, 2 is the only even prime number. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and we can keep going, but this is it for now. That's all we really need. So if I do the greatest common factor of 120 and 256, and I want to do it with factor trees, I take the number 120 first, and I go to my first prime number, which is 2. And I say, okay, if I do 2 times what is 120? Well, that's 60. Then I look at 60, and I say, is 60 divisible by, and I go back up to my list again, 2 is still at the front, so is 60 divisible by 2? Yes. So I can take 2 out once more, and I'm left with 30. Is 30 divisible by 2? Well, yes, it is. So we get 2 times 15. Is 15 divisible by 2? No. So when I get a no, I move into the next prime number, which is 3, and I say, is 15 divisible by 3? And I'm like, yes. So I do 3 and 5. And now at this point, all of my numbers, so I've got 2, 2, 2, 3, 5. So all my prime numbers are there, and I can't divide any further. So I can say that 120 is equal to 2 times 2 times 2 times 3 times 5. This is called prime factorization. I'm writing 120 out as the product of prime numbers. And then I do the same thing for 256. So 256 is even, so I can divide it by 2. So 256 divided by 2 is 128. 128 is divisible by 2. So that would be 64, which is also divisible by 2. So that would be 32, which is also divisible by 2, which is also divisible by 2, which is divisible by 2, which is divisible by 2. So there's a lot of 2's here. So basically 2 to the power of 1, 2, 3, 4, 5, 6, 7, 8 is equal to 256. It's equal to 120. So I've got 2 times 2 times 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 7, 8 equals 256. Now my GCF in this case is what is common between my two lists of prime numbers. So I have 2 here and a matching 2. Another 2, another 2. And that's it. That's all that matches. 3 and 5 doesn't have a match in the other one. So I would say the GCF is equal to what matched. So we had 3 2's that matched. So 2 times 2 times 2, which is 8. So 8 is my greatest common factor. 120 and 256 are both divisible by 8. So factor trees are a great way to try and find that greatest common factor. particularly if like you're not too sure, like of the factors, all you have to do is divide by 2 and then 3, then 5, then 7, and so on until you get only prime numbers left. The other one is to do the list, and this is what we've been doing so far. So like the factors of 24, 1, 24, 2, 12, like and so on. Same thing with 56. And then you look at your list and you're like, what is the biggest number on both lists? In this case, it is 4. So 4 is the biggest number that appears on both lists. So if you prefer lists, that's fine. If you prefer factor trees, that's fine. I'm going to ask you to do both in class. So we're going to have a worksheet on both of those. But when it comes down to it, unless I'm asking you specifically for one method, you can use either one. Okay, so we need the greatest common factor of 27 and 54, or of all of these. So pause the video, come back when you are ready to see the answer. So 27 and 54, greatest common factor is 9. So 9 times 3 and 9 times, oops, maybe it's not, it's bigger. 3 and 6. So we can GCD of 27 and 54. Oh, it's 27, of course, stop. 27 times 2. I was like, wait, no, something's not right. So yeah, it's 27. So 27 times 1 and 27 times 2. For the second one, for 15 and 100, it's going to be 5. So you'll have 5 times 3 and 5 times 20. For 22 and 121, that's going to be 11. So we got 11 times 2 and 11 times 11. So 11 is my GCD. 17 and 102. Remember, 17 is one of those prime numbers I listed. So unless 17 is a factor of 102, the greatest common factor is going to be 1. So I do 102 divided by 17. It is actually divisible. It's 6. So that means 17 is my greatest common factor. So it would be like 17 and 1 and 17 and 6. So 17 is my GCD. If two numbers are co-prime, so say I put up 3 and 11, and I said, what's the GCD? You'd be like, well, their only common factors are 1, so the GCF must be 1. So this is what we call numbers that are co-prime. And they don't have to both be prime numbers. Like I could do 3 and 10, or let's see, so like 77 and 10. So both are not prime numbers. They have factors, but if I do their factor tree, I get 77 to be 7 times 11 and 10 to be 2 times 5. So they're all primed down, but nothing is common. So the only common factor then must be 1, because you can multiply anything by 1 and it stays the same. So 1 will be a common factor regardless of what we got, but it may not be the greatest common factor. All right, when it comes to polynomials, not much changes. So we still look at the coefficient, the number part, and we say, okay, coefficient of 12, that'd be 3 and 4, and then that's 2 and 2, so we got 3 times 2 times 2, and then x and y, the variables you can't do anything with unless they're squared or cubed. You just leave them as they are, because we don't know what they are. So in 15, we got 3 and 5. So that's done. So we're going to have 3 times 5, and then x squared is x times x. So we just break it up. And then I look for what's common. So I've got a 3 in both lists, and I've got an x on both lists. So I would say my GCF is 3x. That's it. Try it out with each of these. Pause the video, come back and see what the GCF is. All right, for the first one, greatest common factor of 15 and 20 is, see, it's 5. So we got 5. And then letters-wise, I got an A and a C, an A and a C. So A and C is common to both. For number 2, 124, they're both divisible by 4. So I'm going to get 4. And then x squared is x times x. So there's a 1x common to both. So I got 4x as my greatest common factor. For 3, 4a squared, 2a cubed, 2 is my greatest common factor, and we got a. So I got 2 a's common to both. So I would say a squared is my greatest common factor. Minus 10 and 20, 10 would be my greatest common factor. The variables have nothing in common. and then 56x squared yz and 64xyz. I would say 8 is my greatest common factor for the numbers, and then x squared is xx, yz. We got xyz, so there's an xy and a z common to both. All right, so what is a factor tree and how does it help us find the greatest common factor? A factor tree is when we start dividing a number up using prime factors. And we start at 2 and make our way up through the prime numbers until there's nothing left to divide, everything is prime. And then when we are trying to find greatest common factor, we're looking at both lists of prime factors, circling or highlighting the ones that are common, and then multiplying those, and that gives us our GCF. So for tonight, I assigned a Khan Academy at the start before we started class while we were waiting. So this was just to practice finding greatest common factor of 2 numbers. It's a 6th grade math skill, but I wanted to recap it anyway. And then we've got a worksheet in class where we are doing the GCF of 2 polynomials, or algebraic expressions. So they're going to have 2 values, numbers, and letters combined, and you're going to have to tell me what the GCF is. You'll be able to find that in Schoology. Thanks so much for being here. I'll see you soon.